In part 2 of this series, I'll show you how to assign formal charges to atoms in molecules. We ended off with question 2, where we're expected to assign formal charges for each atom in the resonance forms of N2O. Which resonance form is likely to contribute most to the correct structure of N2O? Now, unlike in question number 1, as you can see, we're not given the resonance structure. So we want to start by creating the resonance structure for N2O. So we'll start by writing out the valence electrons for the atoms here. We have 2 nitrogens, so 2 times 5, plus 1 oxygen, and that has a valence of 6. This sums up to 16. We have to determine what the central atom is, and normally what we do is we look for the most electronegative atom in the molecule, which is oxygen in this case. However, nitrogen has a higher valency than oxygen. In other words, you have 3 electrons that are unpaired in nitrogen, whereas in oxygen you only have 2 electrons that are unpaired. And the reason why I said it's higher is because I subtracted 8 minus 5, which is 3, and 8 minus 6 is 2, so 3 is bigger than 2. As a result of that, nitrogen will be in the middle for this molecule. So we have nitrogen, and then you can place either oxygen here or here. So nitrogen and oxygen. Bonds need to be formed here, so I'll put lines in between these 2 nitrogens and the nitrogen and oxygen. This means that 4 electrons are already used up. We have 12 more to work with, and those 12 will be distributed among the peripheral atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This has a complete octet, that has a complete octet, but the central nitrogen does not. To remedy this, a few things can happen. Rather than these 2 electrons being here, they can be bonded between the 2 nitrogens. Now let's do a count. We have 1, 2, 3, 4, 5, 6, 7, 8, but this nitrogen still has 6. So I can move these 2 electrons here, and now we have 8 electrons around this nitrogen, 8 around this one, and 8 around that oxygen. This is one resonance structure of 3. Let's take a look at another one. So beginning where we left off last time, rather than having 4 bonds around this nitrogen, I can bring these 2 electrons here and these 2 electrons here. What happens now is that we have 8 around this nitrogen, that's a complete octet, 8 around this, and 8 around that one. So that's a second resonance structure. The last resonance structure could look like this, where these electrons around this oxygen can be placed here, and these can be placed here. As a result, this has a complete octet, that has a complete octet, and so does that. I'm going to label this 1, this 2, and this 3, and I'm going to create a table similar to how I did in question 1. This column will be for 1, 2, and 3. And I'll write down N, N, O for each of these because that's in the order that they're in. Let's write down the number of valence electrons for each of these. Of course, we already figured that out. It's 5, 5, and 6. Next, we account for the number of lone pairs. This has -4. This has none. This has -4. I'm counting the dots. This has -2, none, and -6. Here we have -6, 0, and -2. Lastly, the number of bonding electrons. So for this nitrogen, it's 1, 2. Write it down as negative. For that, it's -4. And for this oxygen, it's -2, -3, -4, -1, -1, -4, and -3. Now we add up the columns. 5 minus 4 is 1, minus 2 is -1. Adding these up, we get +1, that's 0, that's 0, that's 1, and that's -1. That's -2, +1, +1. Now you want to choose the structure that's closest to 0. Take a look, we have -2, +1, +1. That's too erratic, we'll just ignore that. Then we have to decide between 1 and 2. Because this structure, specifically this oxygen, has the -1 charge, and because oxygen is most electronegative in comparison to nitrogen, this one is the one that you choose. Whereas over here, the oxygen was neutral and the nitrogen was negative. So we are less likely to see this and more likely to see this structure. And there you have it. That is how to assign formal charges to atoms in molecules.